So the last time we discussed inductance or the transmission line parameters. And we mentioned there are 4 transmission line parameters. What's the first parameter that we discussed? Resistance. And then conductance. We mentioned about resistance is the power loss over the I square will give you R. So it's basically is a power loss, real power loss. And then we mentioned about conductance G on the transmission line. When we represent the transmission line, we represent it as resistance and conductance. Conductance means in shunt. There is a resistance connected in shunt. What does it represent? It represents the leakage current. Leakage current through the insulators, because the insulators will get dusty. Then these insulators will have, or maybe the age of the insulators also plays a role of this one. The high voltage, these insulators are under high voltage, so these insulators becomes weak, and these you call them leakage current. So this is losses. Any current goes somewhere, it will be a loss or power loss. So it will be a loss. The second part or the third parameter is inductance. Inductance is generated because we have magnetic field. Why we have magnetic field? Because it's an AC, alternating current, goes up and down, up and down. And also we have what? The AC, and also we have other conductors nearby for phase A, phase B, phase C. Or even if it's single phase, we have one conductor and the return conductor. So there are 2 conductors close to each other, then we will get inductance because of the magnetic flux linkage. So that is magnetic field. Then we represent, so we add an inductance. What does it cause, the inductance? It causes voltage drop. Okay, not real power loss. It causes voltage drop. So I square X, that is voltage drop. Then we need to include the inductance. The 4th parameter is the capacitance that we're going to talk next lecture. So today we will focus on the inductance, and we mentioned the last time about how to calculate the inductance, and we mentioned about we started from magnetic field intensity. You see now, so it comes to your mind, if there is inductance, it comes to your mind magnetic field. And then from H, we multiply by H by the permeability, the mu, we get B, flux density. And from the flux density, we get the flux linkage. And then we get the inductance. So if you read the textbook, you will see the orders like this: magnetic flux density, then density, or magnetic flux intensity, then the density, because of the area, cross-sectional area of the conductor, and then it comes the flux linkage between conductors, of course, lambda, flux linkage. Then from the flux linkage, we can determine the inductance. So what you would need to know to focus on this lecture is how to determine the inductance of a transmission line. Remember now, a transmission line can be just a single phase, one wire and another wire nearby. Or it could be 3 phase, 3 wires. Or it could be 3 phase on one side and another 3 phase on the other side of the tower. So we have 6 wires altogether, and each wire or each phase will have maybe more than one conductor. Then it comes on and on. So other conductors. So please focus now how to determine the inductance of a transmission line. Okay. So we started with the inductor itself. The inductor is a solid inductor, and then this is the inductor here. We have the length of the inductor. So this is, for example, is 1 meter length, because this will be per meter. So we calculate the inductance per meter. From the magnetic flux density, we can get the current. Current is around here. So we integrate the flux intensity, we get the current. And then from the current, we can get from the flux density, intensity. Flux intensity, the units is ampere per meter. You see, current per meter. So how much per ampere per meter? This is, we call it flux intensity, شدة flux. Magnetic field intensity, not flux. Magnetic field intensity. If we multiply this magnetic field intensity by mu naught, the permeability of the material, or mu naught is the permeability of through air. What we mean permeability is that the magnetic flux. Remember now, the magnetic flux is around the conductor. Around the conductor. When the conductor, you remember this is the right hand rule. Conductor is going through this one, then the magnetic flux is around, like this, around. If the current is going this way, then the magnetic flux on the other side, the magnetic field, magnetic field. Okay, so from the flux, from Weber per meter, flux density, you see, then we get the flux itself. Flux. Phi here is the flux. From the flux, we can get the flux linkage, as you can see here. So we just derivation like this. The lambda, what we are looking for here, we're looking for the flux lambda. This is what is our goal here, to find lambda, the flux linkage. From lambda, if we divide by the current, we get the inductance. So you will not be asked, of course, to determine these, but you will be asked the units of each lambda, b, and what they represent. So you need to know these, what they represent. What is lambda, for example? This is flux linkage. And then the internal, we got internal inductance. Internal inductance is inside. So what will be the internal inductance? As you can see, so we just divide by the current. And this is the flux linkage. Half times 10 to the power of minus 7 times the current. So it becomes constant. Therefore, this becomes 0.5, which is 1 over 2, times 10 to the power of minus 7 Henry per meter. Okay, Henry per meter. If you multiply this by omega, you get the ohm per meter. So that's the ohm per meter. So therefore, that is our focus here. And what is the internal inductance is constant. Becomes constant. 0.5 10 to the power of minus 7 Henry per meter. We have a conductor. So this is the internal inside. Then, if we want to go outside the conductor, remember this is the solid line here, solid circle, is the conductor itself. And the magnetic field intensity is the dashed line here around. As you can see, it's a loop. If we talk about inductance, we're talking about this loop here. It's around, it's a circle. And then we put the arrow. This is what? Magnetic field. If we talk about electric field, then you will put plus, minus. And you will put a line. Okay, you will put a line. So it is a direction. So what's the plus and minus plate? Plus plate, plus. That's why we represent the capacitance. So this is the capacitance when we draw, or magnetic field. can write maybe capacitance or electric field, magnetic capacitance, or we call it electric field. No? Electric field. This is magnetic field, like this. So when you represent magnetic field, you represent it this way. Okay, this way. I'm talking about the circle itself. Okay, you present it as a circle, magnetic field. So when we calculate the inductance, always think of a circle. When we calculate the inductance, the capacitance, think of positive and negative, one from two. All right, and then we get what? We get the Hx, so magnetic field intensity again, ampere per meter, where x is greater than r. What does it mean? R is the radius of the conductor. The radius of the conductor, and x is greater than r. So this is outside. Outside. So it is either D1 or D2, whatever is the point here. So we want to find, for example, here, this part here, this point here. This will be 1 over 2 pi x. So x is D. That's outside D2. All right, then we go on. And these are derivations, so you can go on again. Now we find this is the way now. It repeats itself. From the magnetic field intensity, we get the flux density, and then the flux. From the flux, we get the flux linkage, lambda, as you can see here. Okay, and then we get what? The flux. This is the flux linkage. If we divide by the current is here. Huh? The current is here. Then we get the inductance. If we divide by we get the inductance. So the inductance of outside will be D2 over D1. You see here? And remember now, natural log, it comes from where? Just to remember, to know now, as an engineer, you need to know the theory. Why we have this natural log, for example. Why we have this equation looks like this. This is what engineers need to think like this. Okay, why we have the equation looks like this. This natural log comes from 1 over x. 1 over x, this one here. Okay, I over x. This is I over x. Okay, and then when we divide by I, then we get like this one here. So lambda. Then we get the integration of 1 over x is natural log. Remember now the flux linkage, we integrate. Okay, we integrate the flux. Okay, so therefore, that's why we get the natural log. So don't forget that you add this natural log from where? Because we have this, we integrate 1 over x. The integration of 1 over x is a natural log. Of what? Of the limits of the integration. D2 over D1. As you remember now, it's D2 over D1, the upper. This means it's from D1 to D2 in here. So this is the flux from D1 to D2. This is outside now, talking about outside. There is a magnetic field. That's why if you brought, for example, a compass or your mobile phone, for example, you want to know where is the Qibla. And you are close to electronic devices. These are magnetic fields also. Wires, conductors, you are close to conductors, for example. You have wires close to you. You have lights maybe or ACs, wherever you are in the room. So you need to go to get the correct direction. You need to go to a space that there is no interference from magnetic field. No interference from magnetic field, then you get a correct direction. Because if the compass changes according to what? According to the magnetic field. Okay. All right, so therefore it's D2 over D1. So outside the conductor, there is a magnetic field. You can feel it, you can measure it. And here is D2 over D1. The space, it's the limits. Okay. From D1 to D2. The integration from D1 to D2. So this is, we know now it's from D1 to D2. Otherwise you get different if you are integrating from different from D2 to D1, it will be different. All right, so that is and then we just divide by the current. You see now the current is by itself is multiplied here. It's a function. The flux linkage is a function of the current. So we just divide by this current here. We get the natural log, or we get the 2 to the power of 10 to the power of minus 7. And remember now for the internal there, when we add it, then we get this D2 over D1. So this is what? This is the inductance between 1.1 and 2. Between this point here, this point, and this point. Okay, between D2, with D1 and D2. Therefore, we get the inductance. All right, and so we can go on. Now, if we have, now, if we want to find the inductance before we go to it, if we use the identity, half equals 2 to the power of 2 natural log e to the power of 0.25, 1 over 4. Is more convenient expression of lambda at a point P. Lambda at a point P, for example, here, this one. So this lambda at a point P is outside. Any point here, outside. Remember now the solid is the conductor. Anything outside the conductor is a point that we want to measure. Okay, so the total flux lambda P linkage, total flux linking the conductor out of to external P at distance D. So there is a point P at distance D. Okay, point P means this is a point here at distance D. This is the distance which is here, and in this case D2. Okay, is the sum of the internal flux linkage and external flux linkage. So we have internal and external. That's why you will see these plus internal and external. And to make it more convenient, we use this identity. Half equals this one, so to get rid of the half. Therefore, we can do it like this, and so on, and then we come to the inductance at a point P. It will be 2 to the power of 10 to the power minus 7 natural log D over R prime. Remember now it's R prime. What's R prime? R prime comes from this natural log 0.25. So therefore, here e to the power of negative 1 over 4. Okay, so this will give you R prime. 0.7788 radius times the radius, so it's smaller than the radius. Okay, so there is not the full radius for the conductor, radius of the conductor. So the radius of the conductor is R. Okay, and we need to multiply R by 0.7788. Why we need to multiply this? Just to make it convenient there, instead of doing this addition here. Instead of doing these additions like this equation, we can make the equation like this, just in one shot here. 2 times 10 to the power minus 7, the natural log D over R prime. And R prime is the radius of the conductor times 0.7788. Where do we get 0.7788? We get it from e to the power of minus 1 over 4. Where do we get e to the power of minus 1/4? We get it from the identity here, to make it convenient to use. This is the idea, just to make it convenient to use. So don't forget to divide by R prime, not the radius. You will be given the radius in any table. You will be given the radius of the conductor. Don't forget to multiply this radius by 0.7788 to find the inductance. And you know now the details why we need to find 0.778. Okay. So we can go on. So this is the inductance that we want to find. Again, this inductance is the inductance at a point, any point. What is the distance from the center to that point? This is what is D called. The distance between the center of the conductor to the point over the radius of the radius times the R prime times 0.7788 over the radius, and that's the natural log. And this will be Henry per meter. Again, now we are talking about Henry per meter. This is per unit length. And then how long is the conductor? We just multiply by the length of the conductor. We get the inductance. So the inductance depends on the radius of the conductor and the distance. How far the point that you want to measure the inductance. Okay, so the inductance depends on the radius of the conductor and the distance between the center of the conductor and the point. All right, so that's the inductance now outside. Remember now the inductance inside the conductor, internal, we call it internal, the inductance is constant. Outside, it depends on the distance and the radius. But don't forget to multiply the radius by 0.7788. And then if we have M solid cylindrical conductors, so we have a number of solid cylindrical conductors like these. For example, we have M solid cylindrical. Remember now this solid cylindrical. We will come to stranded conductors. Why we are doing this actually instead of because you are an engineer, you need to know the theory behind this. This is the idea, so you can go on. So when you read this one, then you will remember what you are reading. All right, so these are M. Array of capital M conductors. M is capital. So it's from 1 to M capital. This conductor here is conductor number M, small m. Conductor number M, small m. This M, capital M, is from 1 to M. Okay. And this is in your textbook, figure 4.8. Okay, again, now from the flux linkage, it comes, of course, for the flux linkage on there, dPm. So we want to, for example, to find kPm. Okay. We want to find delta lambda K, which is conductor K. P is a point P from P with the effect of M. Number M effects on what? On K. So what does this mean? It means what's the effect? What is the flux linkage, okay, of conductor K? The effect of what? Of conductor M, because we have a number of conductors. What's the effect of conductor M to K? That's another conductor. From a distance of P. The distance is P. Okay. Therefore, we get this dKm. dKm. So the point here, this point here, we want to find this point here. We want to find the inductance at this point, P. Capital, this is P. Okay, this is the point. We want to find the inductance. What inductance? Inductance of the effect of conductor M to K, because every conductor now close to each other will have an effect on each other also. So it's not just one conductor at a point. If we have just one conductor at a point, then we already discussed about the distance. Then here is only the effect, because we have another conductor, so the effect of conductor M to K. Then we have an inductance here now. Where we are measuring at point P. So we want to find the inductance here at this point. Due to what? Due to the effect of conductor M to this, not just the effect of conductor M to this point, the effect of conductor M to K. So conductor M has an effect on P. That's by itself. Then we have also conductor M has an effect on K. So therefore we have an inductance. Okay, flux linkage. We have flux linkage between M and K. This effect on K, we want to measure it at point P. This is the idea. Okay. Okay, let me see your. Are we neglecting self-inductance here? No, we are not neglecting. We are calculating the internal, the outside. To detail later. We are calculating the outside. Okay. Later you will see it's all together. Okay, all together. This is included. Okay. How do we know it's included? From here. That we already discussed this now. Instead of having this 4, we're talking about this one, so we make it convenient. Instead of having the plus, that's the equation where the plus is somewhere. Okay? That's why we talk about this inductance here. So to get rid of this plus here, the internal inductance. So that's already, to get rid of this plus, we came into this equation. So this is included now. That's why we have this R prime. That's why we have R prime, not R. Okay, so we added the internal with the external. Here we are. This is the equation that I was referring to. We added the internal to the external. Remember now, in this external we have R, the radius R. But good question that you asked. R, this is radius, not R prime. And when we want to add this internal and external, so the effect of, instead of having these into this equation, we can have this half here 1/2. We can put it like this. This half here, we can put it like this. This half here, as you can see, we can put it 2 natural log e to the power of 1/4. Then, why we put it natural log? Because we wanted to conform with this natural log, with the other natural log in this equation here. This equation has a natural log. This equation has no natural log. So therefore, I can convert this into natural log. I can combine them together. So therefore, I combine them this way. Okay, because of this R prime, then this can be written like this. Okay, so this is the plus here. Okay, because the plus here, you cannot add natural log plus this one. Then you make it on natural log over like this. Okay, so D over R prime times this one here, e to the power of minus 1/4. Okay, so therefore this radius here of the conductor will be reduced. Therefore we can write it as R prime. Then it comes to your mind, this is included now. The internal inductance is already included in what we are calculating. So we don't need to find the internal inductance when we write R prime. Okay, R prime, which is what, 0.7788. What about total effects of other wires? Yes, then we need to add them, exactly. So what the question here, what was the total for other wires? Exactly, so we need to add them one by one. You see how complicated? No, this is R prime is only the radius. I'm not talking, the other effects is outside, talking about the radius of the conductor. Okay, now this is the radius of the conductor here. Okay, the radius of the conductor. We're talking about a point and with the radius of a conductor. If we have more than one, it will come later when we do 3-phase. We have other conductors. Then we need to take the geometric mean distance and geometric mean radius. Okay, instead of R. Okay, so we'll take the geometric mean radius, geometric mean distance. We're talking about now the effect only on one point due to this one. Okay, therefore we have this inductance. So we can go on. That's the same thing here. You get from the flux linkage. So you see now we're adding all these conductors now for each conductor will have an effect. We can go on and on. What I'm giving you here is the idea, so you can read it. You cannot go one by one. It's not, you are not in school now. I'm giving you the idea here of how to read these equations, so you know the theory behind these. What we're doing here, we are adding all conductors, the effect of all, removing, okay, adding all the conductors, and then until we come to this part here. This is our, so that's what we have the summation now, because we have so many conductors as you mentioned. Therefore, we add it like this: m equals 1. So we add it until m. How many conductors we have? We have capital M from 1 to m, capital M. Okay, so this is only m is the number of a conductor. M is varies from 1 to m. I don't know why your textbook put it n. It should be maybe another number, but it's okay. And why we do not put it k? K is the conductor K. Okay, this is the conductor K, the flux linkage on the conductor K regarding all conductors nearby. Okay, all the conductors nearby, we add them like this. And this is what we have. So this is the flux. And then you will just divide by, then you will get the inductance. Now, inductance of a single phase line. Now that you see what we have is just is to know the theory behind this. If we have more than one conductor, now we have two conductors behind. When we say single phase, it's not one conductor, it's two. One is forward, one is backward, or one is return, and one, because every wire must close the circuit. You see, when we draw a circuit, we draw a line and then back to the source. So we have two lines. Okay, back to the source. Go to the load and then back to the source. So we have two lines. Therefore, when we talk about single phase, we have two lines. And this is the way we do it. We add them here. XX is what is the radius of XX. DXX, R prime X is the radius of the conductor. DX X is the conductor of X, the distance of conductor between X and X. DXY is between X and Y. So DXX is for the conductor X, the geometric mean distance of X. Therefore, DXY is D actually. DXY is D. That's why we write, you see, we add this one here. This is conductor X. It has a radius, as you know, it has a radius dx. X and also dxy, because it also has an effect from y. Therefore, we need to add it. This is ix and this is iy. This is the current of iy, of the current on y. We have two conductors. One is called x and the other is called y. Okay. Now this is the radius of x, xx. So we put it r prime x. This is the distance between x and y. We put it d. So this is the distance. So dxx means that the radius, just conductor x. Okay. And xy is the distance between x and y. Then we can put it like this way. Okay. So this is just to play with the sign, put it there negative, so you can subtract from here, and then we get it again. This is 0.778. Remember now, E prime, this is R prime here. Put it, and then we get this inductance. You see that at the end you will get this inductance, Lx or Ly, doesn't matter. Same, because they are the same size. If they are the same size, we put it this way: 2 to the power of 10 minus 7. Natural log, and we already know why we do natural log. We already discussed about the integration of 1 over x before. D is the distance between the two conductors over the radius of the conductor. So if it's the radius of the conductor here, if the two conductors are different in radius, then you need to take care of Lx will not be the same as Ly. Lx will be different than Ly. Here, per conductor, you see, Henry per meter per conductor. This is the what? The inductance of X. Therefore, you put it inductance of X conductor. So this is per conductor. If the radius, if you want to find Ly and it's the same, then for Ly will be the same, exactly the same. But if the radius of Y is different, then you need to change this one here, Ry prime. Okay. The distance, of course, is the same from HUD. And also this will be Ly. And because we have conductors, then okay, single phase 2-wire line, that's what we discussed. Single phase 2-wire line, and for Y will be the same. As we mentioned, if they are the same, then we add them. This is Ly, will be per conductor. This is Ly, and that is Lx, the same. Okay? 2 to the power of, okay? This is for Ly. Conductor of the inductance of conductor Y. Okay, there Ly. That's what we discussed. And then we add them if we want to find the inductance. This is the inductance that you draw on circuit. It's L, not Lxy, not Ly. That's what the inductance you draw on the software that you are using. What inductance you're drawing? This L. So when you draw the inductance, you already calculated, the engineer already calculated these before. And then they give you this inductance. Okay. So that is Lx plus Ly. So therefore, 2 inductor because you have single phase. Lx over Ly. The Lx plus Ly. Therefore, that's why we put 4 here. And this, the plus, we can put it this way here, like this. And then the natural log can be this. When you add these natural log, we can put them in this way. Okay, d squared over r prime x times r prime y. Okay, the addition, you make it if you put it under one natural log, you multiply them. Multiply d plus d times d when you add it. Okay, so don't forget this. You're adding here if you put natural log, or you can put it just in one form like this: d squared over r prime x r prime y. What's this? This is the total inductance. So that's the inductance that you use. So this is H Henry per meter per circuit. Okay. And that's what you mentioned there. That's what you draw, Lx and Ly. Okay. So that's why you will put it like this. So this is the and then when you write it as ohm, you will just multiply the by omega. Okay. 2 by f. 2 pi the frequency, 2 times pi by the frequency if you want to calculate it, and you use it in circuits. So this is okay. Okay, so don't forget this R prime again. Now this R prime, we're doing the inductance, and we know now why we have R prime. Now we have 3 phase. خليكم معنا حلوين كده. That was single phase, and we know how to calculate the inductance. Now we have 3 phase, 3-wire line. Single phase, 2-wire line. Not single phase, 1 wire. Single phase, 2-wire line, we write it like this. Now 3 phase, 3-wire line. خليكم معنا حلوين صحصحين. Here in this, it depends on how we connect it. How we connect the 3 phase. If they are connected in a triangle form like this, phase A, phase B, and phase C. If they are connected this way, they will have what? This equation here. 2 to the 1 d over r prime. D is the distance between each conductor, and they have the same distance, exactly the same. If it's different, then we use the other one that we calculated about m, from 1 to m. Then we need to do all the calculations like that if they are different. Okay, so we have one calculation, and then you will do the summation. Okay, the previous slides that we discussed, you have conductor from the conductor 1 to M. Now what we have here, we have they are all equally spaced. So if the three phases are connected like this, which is you will not find it like this, because it's what the tower, we do not connect the tower. We usually connect the tower, by the way, but this is impractical. We connect the tower. We connect the tower like this. And this is down all the way. This is the tower. So these are not equal. So we have a tower here, we have a conductor here. They are not equal. But if you want to make a tower like this, then becomes, that's why they do not, it becomes complicated, more expensive for them. It's so easy to have just one column and then put it like this. And we will discuss the three phases when are connected this way. Here, why we're doing here is just to show you now if they are connected in this way nicely, in this way, which is you will not find any conductors like this in the tower. Becomes more complicated, expensive to connect, to put a tower like this, one top and one bottom, two bottom like this. Then you will write it this way. Okay, so this is an inductor if it's connected this way. Again, now you are not a technician, you are an engineer, so you know that's why you need to know these. Although in practice the towers are not connected like this, but in case something, you have it like this. Okay, so you know now the theory behind before we go. Then you will have only one D here, and again now R prime and 2 to the power. So this is D. So these are Henry per meter per phase. This is per phase. That's why when you write, when you write in the software, Powerwall Simulator or circuits, you represent only per phase. That's only per phase, the inductance, etc. What about three phases? The three phases will be similar. The other phases will be similar. The inductance of phase A will be similar to phase B, will be similar to phase C. Okay, that's why we call it a single line diagram. A single line diagram, we represent the three phases into just one line, one phase. So instead of drawing three phases in your software, we draw one line. This one line is for three phases. Okay, so it is like this. So we assumed all phases are the same in this case here. Okay, of course they are the same now. So LA will be the same as LB, will be the same as LC. And we will see later. We'll see later when they are different what we need to do. Okay. All right, so that's the inductance of conductor A, the same as conductor B, the same as conductor C. So we don't need to include them. So that then we represent the as per phase. Okay, and this is just a solution that you will follow. That's it. You will just plug in the numbers here. Whatever, 60 hertz, three phase, three wire overhead line, solid cylindrical conductor. We did not discuss the stranded yet. This is solid cylindrical. That's why the inductance is constant there. This is a solid cylindrical. Okay, solid cylindrical conductor. We write it as R prime, the radius prime, times 0.7788. Okay, this is R radius of the conductor. And here we have two. We have what's called solid cylindrical, and another is stranded conductors, not solid. So this we assume it's solid, the conductor. And you just plug in the numbers and you will get the 2 pi f, you will get the ohm. Per kilometer, how do we know it's per kilometer? Because it's written here, that's per meter. Henry per meter is given. Therefore, you can convert it into per kilometer. We just multiply by 1,000 here, as you can see. Okay, so that's the inductance. The conductor diameter is blah blah given 0.5 inch. You just plug in here 0.5 inch. You call you 0.5 over 2 blah, because that, by the way, this is diameter. So you need to divide by 2 because you are looking for the radius. And then we just change it into feet. Okay, so we get rid of this 12-inch, 12-inch. Okay, 1 feet over 12-inch. So we make it into feet. Okay. Why? Because this is given in inch, and this is given in meter. So which we convert meter into feet. Please make sure that the conversion is correct. What is given in, by the way, L is given in your textbook Henry per meter. You see there are calculating per meter. Okay, Henry per meter. This equation here is Henry per meter. But sometimes, or most of your time, or most of the times that this is the textbook, it's given in inch, and this is given in feet. As you can see, the spacing of the conductor given in feet and inch. So you need to convert into meters. Okay, you need to convert into meters, and then per kilometer just multiply by 1,000. Okay, otherwise it will be 0.00 Okay, so please make sure that you write this. Okay, so this is end of the chapter, and we don't have time to go for part 2. Anyhow, I'll stop here, and if we have any question before we go. Okay, yes, Tamim.
Please go back to the slide, the previous slide. Yes, Doctor, the unit conversion. Okay, we understood that we converted from inches to feet. Okay, but the calculation.
And then into meter, and then into meter.
But where did it?
For a feet, you don't.
Meter.
And then you will put it into meters. If this is the meter, well, you will put it in the meter. This is what you calculate. This one. This becomes 1.65 10 to the power of feet. Correct. So this the radius is feet.
Yes, and then how it was meter, yes.
And this one, okay, this is what 4 feet. So this is feet over feet, okay, because this is given in feet. Okay, this is okay. And here, this one here is given in feet. Equal triangle, 4 feet conductor spacing. So D is given in feet, correct? And R prime, we put it into feet also. So feet over feet. Feet over feet, so they cancel. And this becomes Henry per meter. This is Henry per meter. So we did not, here you do not need to convert into meter because it's feet over feet. So we convert it into feet, or you convert it into inch. Therefore, you will put this into inch for feet. You convert it into inch, and you will put this is exactly the same as feet. Okay, so just to answer a question, here we do not need to convert into meter because feet over feet. Okay, the result becomes Henry per meter, but always Henry per meter because the equation here is valid for Henry per meter per phase. Okay, so D and R prime should have the same units. So whether you convert it to feet, you convert it to meter, convert it into inch, whatever, centimeter. So these must have the same units, so you can cancel. And the result will be Henry per meter. If the result is Henry per meter, then you want it per kilometer, you will multiply by 1,000 per kilometer. You also multiply by this one if you want to find X, the reactance by omega, 2 pi f. And the result will be per kilometer. And that's what they write, by the way, on the conductor. They write it by per kilometer or per mile. They give you per mile, they give you per kilometer. The resistance, as you saw on that, there is a resistance per mile. Okay. The distance, they usually give it into feet, per feet, not per mile, because the distance is close. Distance between the conductor and the conductor. But the resistance or the inductance, they give it per mile or per kilometer, as you can see here. Instead of having this Henry per meter 10 to the power of -6, we want to get rid of this by -6. So we make it into kilometers. So multiply by 1,000 and we get 0.415. It's okay. No problem. Okay. All right. Any other question? All right. Take care. Thank you.